this having to keep up with stuff, and really is rough for a teacher. But back to this, what an ellipse is, and then, oh man, I don't know if we'll be able to have someone hold my computer and actually when I go through the demonstration with the string, get this on there. I might have that. Anyone want to be an assistant today? That's great. I have 28 students here. Not one person raised their hand. Love it. All right, so I'll just make someone in this last row actually hold the computer as I do my demonstration. But okay, so sorry, cutting in the movie here real quick. We did do a circle question, and we're just talking about these terms that are important, and you feel free to pause the video and write all that stuff down. I didn't even let the class write all this stuff down yet. I'm going through a demonstration about how a circle, the distance from one center to a point, that's what makes a circle. Well, in an ellipse, it's actually two foci. And I was going through this demonstration of how that works, where this point, D1 plus D2 is a constant. So that means D1 plus D2 should equal the distance D3 plus D4, that sum as well. And then now I'm going to go over to there and actually do this. So I am going to ask somebody, oh, this is going to be weird. And then let's see if I can, yeah. So here you go, right here. Hold this to the so you see this, and I'll tell you if you're on the right spot. Okay, there we go. I'll be right back. I got to get my cats. All right, so everyone should watch this. I got my pen up here. Are you okay? It's not too heavy, is it?
No, it's good.
All right. Okay, so let's see if we're on the, yes, there I am. Nice. This is great. So here's my pad here. 1, 2, 3, 4, 5, 6. I was doing this earlier. And then hopefully I can get this so it's, I have a lot of things to hold here. I need another assistant. There, I guess I'll just put this up here. Don't roll on the ground. Okay, so like I said, for a circle, there's just one center. And then this string creates it. We get that, right? Right. Now I'm going to do 1, 2, 3, 4, 5, 6. I'm trying to get this right in the center. I'm going to fumble. I just dropped my tack. Did anyone see where that tack went? Can someone help me on that? Thanks. Trying to get this where the sticks right there. Good. And now I'm gonna, you don't want to be off the screen here, so I want to get this over here a little bit more. Show how this creates more of an ovular situation. And this is why those distances that I set up on the screen there are true, because it's the string. The string never changes. The string is the string. So that distance stays as I keep this tethered and I start moving the pen around to make this picture. That's why those distances are constant. Our orbit is considered ovular or elliptical. The focus is actually, I think, the sun that wobbles. All right, so the sun doesn't stay like in the center of our solar system. It wobbles by the actions of our other planets and their gravity. That's how we first discovered other planets and other solar systems. That's true, actually, by analyzing the wobble of the sun in that system. So I think that's true, but I know definitely that. I lost my tack here. A wardrobe malfunction. All right. Yeah. Okay. I get a little aggressive on the tether, I guess, there with my marker. All right, and then I'm doing this on purpose, that I'm doing two different types of ellipses here. Two different situations with the foci being a little different. Now, does that look like an oval or does that look more circular? What would you guess? More ovular or more circular? 3, 2, 1, go. Circular. That's because I didn't go very far with the foci. The idea is the closer the foci, imagine the foci don't even exist and you just have one center. That is a circle. So as I just go a little bit and keep the foci close together, you have more of a circular situation. Uh-oh, guess who's holding the computer next? Thank you. All right, go ahead, you hold, and then I'll tell you if you're right on the spot here. Okay, that's not too bad. All right, 1, 2, 3, 4, 5, 6. Now you want to get nuts? Let's get nuts. Let's make those foci really spread out. Now look at that string. And now look at the ellipse, perfect, where you're holding that. When I try to draw this one, this is the ellipse that I get. Very, very, very elliptical. And then when I tether, I have to do it this way, otherwise the string gets wrapped around my tacks there. What would you call that? More elliptical or more circular? 3, 2, 1, go. elliptical. That's a word that's called eccentricity. And I'm going to put this up here right now. And if you wanted to make two like little sketches of this, eccentricity, when I start showing, the numbers here, this is when eccentricity is closer to 1 as a numerical value. All right, you get more of an ovular situation. And then, thank you very much. This one is when, and it's really the distance that I told you the foci are from the center. The closer they are to the center, the more circular this is. This is an eccentricity that's closer to 0. Good, we can't see that. I'm trying to hold the computer as we do this. And I'll show you what eccentricity is numerically and how we find it here shortly. But really, and I spend this time to go over these things because they're important. This is to make you not memorize and be a robot that I've mentioned calling you guys sometimes about memorizing formulas. It's really about what's really going on behind the scenes, which will tell you what's supposed to happen. Like what happens with our equations that we have to memorize, but why they actually should make sense with what's going on here. So this should make sense now. Why is D1 plus D2 equal to D3 plus D4? The string. The string doesn't change. The string is the string. That's the length of it. And it dictates the pen in the way that I just showed you to make the situation happen. Make the drawing happen. Okay, so now here's some stuff you got to understand. Let's make it simple. Looking at our two pictures over on the screen, look at the more ovular, more elliptical. I'm going to actually call these x-axis and y-axis radii. And I purposely made this go wider right-left. So there is going to be a center, and there's going to be an x-axis radius and a y-axis radius. In this case, the y-axis radius is smaller than the x-axis radius. Who is the biggest radius? The major axis. Major, bigger, minor, smaller. Right? We'll see how this shakes out on our equation here. Vertices are the major axis endpoints. Co-vertices are minor axis endpoints. So it's going to be very simple how this graphs. And I'll show you that in comparison to our equation of a circle. So before I show ellipses, I'm going to show your equation of a circle and make a change on it. Okay, but I'll wait for those that are writing all this stuff down. This is all true. Oh no, I forgot to put in the microphone, so the sound is going to be horrendous. Okay, and actually when I walked away from the computer, you couldn't hear me say a word. This microphone's terrible. Oh well. Now you can hear this whenever I hit the screen with this thing. It's like tap, 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 tap. It's annoying. Okay, is anyone still writing? All right. So the ellipse is a set of all points P in a plane, that thing that I told you. All right, the string dictates it. That's what all that stuff between two fixed points. And actually, it's not focuses, it's foci, I've always said. I've heard people say foci, and I've heard people say foci. I don't know. I always say foci. I don't care. Foci sounds weird. Foci seems weird to me too. But I've found through the years, I feel most people say foci. Fumble. Cool shades. Okay, so real quick, before I show you these equations, let's write a circle down. Remember what a circle's equation is. It is, and we're centered at the origin again to start. That's how we're going to do every section. Maybe not hyperbolas, though, because I told you these things start becoming similar, how things look. And you'll see this tomorrow when we change the center. It's almost exactly like a circle, except with a little difference. Let's go back to a circle that's centered at the origin. It's just x squared plus y squared equals r squared. And I want you to know how easy we should be able to tackle ellipses, because it really should be. What I'm going to decide to do is divide both sides by r squared, because I can. Whatever you do to one side, say it. So I'm allowed to. And when I do that, I get a little different format. Same thing, but now I just put the radius values underneath both x and y. And that's what I want you to understand, what's different with an ellipse. For a circle, these radius values are the same. That's why it's a circle. We have one radius. The piece of string is only a center, no foci. The string makes all the points. Okay? So now I'm going to show the two equations and then the two drawings of these two types of ellipses. And you could have started with the equation, maybe put that first, and then I'll zoom in on just this right-left one that's short and wide. So x squared over, not r squared, x squared over a squared plus y squared over b squared. That's saying that these two radius values are different now. And that's what makes an ellipse, and that's what makes a circle, when the radii are not different. That's how simple we can look at this. Now I'm going to zoom and focus on this. This is a right-lefter. This is one that the major axis is right-left. So what this is saying is the x-axis radius is larger than the y-axis radius. So that is why we have a short wide one. I've just repeated myself like 3 times on purpose, right, to really hammer down this significant difference. The only thing you have to ask yourself then is, how do I find this mysterious C? How do I find where the foci are? And I'll show you that in a minute. I'll show you that at the bottom of this page. It's actually a formula, and it's something you're going to have memorized. But if you common sense it out and you look at my drawings over there, and when I cover the formula, I'll tell you why you should remember what the formula is. Okay? And then for an up-downer, this is just saying the bigger number is underneath the y squared. So therefore, it is taller and skinnier. So the bigger radius is underneath the y squared. So really take this circle equation and compare it to these two different possible ellipses you could have to see that minor difference. Because really the graphing of these is superiorly easy. And I'm going to throw that out there for those that missed this. You're missing a very easy concept. Okay? All right. Now notice where the foci are. Where are the foci in the second picture? Are they up, down, or right, left? 3, 2, 1, go. Up, down. So where do you think the foci belong? On the major axis or the minor axis? 3, 2, 1, go. Major. We should understand what major and minor is. Longer, major, minor, shorter. So notice the foci on this first one, which is wider, the foci are on that x-axis. Notice this one's taller and skinnier, and the foci are on the y-axis. That's exactly what happens. There's a reason. I mean, I drew those both where it was an x-axis was the wider one. But I just have something to say about when we show the formula that you have to have memorized. The other reason why the focus or foci must be on the major axis. Okay, so hopefully you wrote all that stuff. It looks like a lot of letters. It looks like a lot of memorization. Bologna sausage. It's all about the radius, finding the radius of each axis. It's super simple. Okay, so then here's some more things. Just some terms. A is the distance from the center to the vertex. It's a radius value. B is the smaller radius value, called the co-vertex. C is the distance from the center to the focus, and now here's our formula. That is found. That actually should be connected with this, so I'll go ahead and highlight that. It's a Pythagorean relationship. There is a really Pythagorean relationship that, a triangle can be drawn, and then we can make this, this is a wax on, wax off. This is the formula to find C. Now here's when I'm going to start talking about why is it a squared minus b squared. I'm going to go back to my drawing as you're writing this down. I will hold the screen. There's a very simple reason for this. Please look over here, though. Look at my demonstration. This is why you should never screw up this formula, ever. Where are the foci? Are they inside the ellipse or outside? 3, 2, 1, go. Inside! They have to be. Do you know what the focus is for our Earth's planetary movement? Here's another reason I'm going to get real silly about this. The sun is actually the focus, and it wobbles, and I think I said that. If you did c squared equals a squared plus b squared, then the focus would be outside of the ellipse because C would be larger than A, and A is the biggest radius that you can have. So you'd be saying that the sun is here and the earth goes like this. Is this what happens? Is the sun outside of our orbit? Yes or no? Think of the sun as a focus, and that has to be inside the ellipse. So C must be smaller than A. That can only happen through subtraction. All right, that is the common sense of it. Then the other common sense is, where does the focus belong, major or minor axis? 3, 2, 1, go. Major. You know why? If I have an ellipse like this and I try to graph the foci on the minor axis, yet again, your focus will not be inside the ellipse. And that makes no sense whatsoever. Does that make sense? All right, so one more time. I saw someone shake their head no. If I tried to put the foci on the minor axis, you more than likely will have foci that are also not inside the ellipse. You yet again are saying the sun is here and here's Earth's orbit. And that cannot happen. That is not what happens. All right, for this truly to be a thing here. Because you're going to find out when we do hyperbolas, there's another formula. It's actually going to have plus in it. Right? And then what people do is they flip coins and then they grab the wrong formulas. They got their file folders all screwed up because they don't think about the things that I cover in class to common sense this stuff out. Just tell me how to get the answer, Mr. Samulus. I'm trying. I'm trying to get you to not make these mistakes. So here we go. Now I hope you can see how this is close to an equation of a circle, but wait a minute. I always have like an r squared here, right? I'll get this going here. But graph the equation, identify vertices, co-vertices, and foci. It's actually going to be very simple. I wish I could zoom in on this a little further. And I bet you half of you will already be able to answer this. What is the x-axis radius, which I think you know will be an A value because this number is larger. What is the x-axis radius? 3, 2, 1, go. It's 12. It's not 144. No one said that, I don't think. Understand that that's a squared underneath there. This is the radius squared for the x-axis. Fumble. And that, the first fumble? Or first fumble. All right. And then B equals, 3, 2, 1, 8. And then you can see right away how this is going to be a short, wide one. And I got to do the best I can with my scaling here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Some scaling issues. Be nice to have a coordinate plane to work with here. I could have put that in the notes ahead of time. That looks like a little too far out compared to the other one, but we get the idea. And we can see how that's not a circle. It's more of an oval, and that's what's going on with this. So A, to graph this, it's so easy. B, now we got to find the focus. To find the focus, it's that magic formula, and then we can put the vertices and co vertices down. I didn't do that in first hour, but we can go ahead and do that now. Focus, though, we'll get this over with. Here's the reason. It's a squared minus b squared. The foci must be inside the ellipse. I almost grabbed the wrong word. So it must be minus. All right, and that's the only way I could think. And you want bigger minus smaller. You don't want a negative out of this, so it's always the bigger radius squared value minus the smaller. And then this allows us to write in exact form because this is 80. And then we're going to root it. And then here, listen to my thought process because you're going to have to do this as well, writing this in exact. What's the square root of 80? All right, well, 80 is 8 times 10, right, everybody? Now I'm going to fumble. I got 10, and I know that's 2 and 5. And I'm going to bring that 2 to the 8. What's 2 times 8? 16. So now I know that this is 16 times 5. That's how my brain works to identify the the perfect square in the product. What's the square root of 16, everybody? 4. So this is 4 root 5. So here's what the foci are. The foci must be right, left, 4 root 5, comma 0. Again, reiterating, all of our starting today, we're going to be at 0, 0 for a center. Then we'll see tomorrow how easy it is when we change the center compared to what we did with the circle. And then we have to complete the square, and that becomes a little bit of a challenge. So that's a challenge tomorrow. All right, so the vertices. The vertices are 12 and negative 12, 0. I guess I could put that here, verts. If you had to note those, you could say plus minus 12, comma 0. And then these are 0, comma 8. These are the coverts. Ooh, covert operation. That was weird saying that. Oh my gosh, my pen, so annoying. So annoying. Those are the coverts. And input, say it. I did not do this last hour once, but I kept saying, hey, we should do input, output, and I forgot. Very simple, and I hope I can still be heard when I turn my face around the screen. You know, it's a very simple concept. What happens when I plug in negative 12, comma 0? What's negative 12 squared, everybody? 3, 2, 1, go. 144. What's 144 divided by 144? 1 plus 0 squared over 64. What's 0 over 64? 0. 1 plus 0 equals 1. True. All right, so input, output actually happens with all of these points. That's why they are solutions. If I flip it around and put in 0, comma 8, 0 squared over 144 is 0. 8 squared, 64. 64 over 64 is 1. 0 plus 1 equals 1. True. All right, so that's why this works. All right, we can move on now. I named the vertices, co-vertices, and found the foci. Real quick, what should I do to both sides? This is supposed to be equal to what number? How many answers are you going to or how many questions are you going to ask? What's the right side supposed to equal? 3, 2, 1, go. 1. So what do I have to divide both sides by? 3, 2, 1, go. 9. Good. You can't hear them with my bad microphone. I don't know if you could hear it with my good microphone. And then I'll write this a little bit larger. You do want to write x squared over 1 so you don't get confused about what your radii are. And then now it's in the format. So here's the thing. Hey, look at that equation. You might have thought that's a circle. No, when you have two different numbers in front of the squares, that makes it an ellipse. Because then when you divide, you get different x and y axis radii. So I do like that. You might have thought that looks circular. Wrong. The 9x squared screws it up. If it was just x squared plus y squared equals 9, then yes, that's a circle with a radius of 3, both x and y axis radius. If I divide it by 9, then it just has the radius squared underneath each. So the radii values are equal. That's why that's a circle. And I want you to understand that as we proceed on with ellipses and knowing these differences. And you should, if you've done your circles correctly the last two lessons. So anywho, what's our x-axis radius? 3, 2, 1, go. 1. Don't say the square root of 1. That always drives me nuts. Square root of 1 is 1. And it's a b value because it's smaller, because what's the y-axis radius? 3, 2, 1, go. 3. So very simple to draw. It's not rocket science. But you know what? It is. This is rocket science. We got to know where where our orbits are by these elliptical equations so that our rockets can hit the planet at the right point. This is so true. Of course, it's a lot more complicated than these beginning incarnations of what an ellipse is on a little coordinate plane. And then why do we put stuff on a coordinate plane is a good question. And that's because that's how humans figure stuff out. They put things on paper and plan, and then they build things to make it, and then they work through that planning. So really, really basic start, but that's true. Very ovular. And actually, I forgot to find one more thing, which was that eccentricity thing. And I can compare these last two with that, or maybe this one and the next one. So I think this eccentricity is pretty great. All right, so what's the foci? C squared equals, again, a squared minus b squared. 9 minus 1, which is 8. And then we're going to square root that. And that equals square root of 4 is 2. 2 root 2. 8 is 4 times 2. The square root of 4 is 2. You should be getting quick with that. All right, and then, okay, I don't get what that is, but you know what? The square root of 9 is 3. The square root of 8 is very close to that. So I'm actually going to go to my calculator. And did I have that before? That's a previous answer. So let's go ahead and do square root of 8, just for purposes of this. Okay, 2.828. 2.828. So here's the foci. We could write it as, okay, it's 0, comma. You better understand that, and that's where you're going to get marked wrong. People not writing coordinates for this stuff. Okay, the foci go up and down, and that was 2.82. And look at where those foci are. That's more like my second drawing, where the foci were really close to those endpoints, over there with the tacks. So very much so. And again, if you went right and left, your foci would be outside of the ellipse if you went the minor axis route for the foci. That's why that doesn't happen. Doesn't make sense. Okay, so just be aware of that as well. Here's the vertices. Here's the co-vertices. You can count. I shouldn't have to tell you what those coordinates are. All right, but I'm going to do this eccentricity now. Here's what eccentricity is. Write this down. It's very simple. Eccentricity is denoted by the letter E, and it's just C divided by A, whatever those those numbers end up becoming from our formulas. Not C squared over A squared, C over A. Now watch what happens, and this is how I told you when E is closer to 1, this is what we get. We get an ovular situation. So what is 2 root 2 divided by 3 approximately? Go into my calculator. So there's the 2 root 2. Now when I divide that by 3, understand first of all how E could never be 1. Actually, if E was 1, something catastrophic would happen, but it'd be close. We can't get C to be equal to A. No, C always has to be smaller than A. So when I do C divided by A, we must have an answer that's below 1. All right, but I'm in the way here, so I think I'm going to delete myself there. All right, so what was that? I'm sorry, 0.94, is that what it was? 0.94 what? Did anyone see the third thing? Oh, heck, I'll just put it back up there. 0.943, okay. So 0.94 is good enough. Closer to 1, this is more ovular than circular. All right, and I'm looking at this last one. It probably would have a smaller than that. It'd be like closer to 0.6, 0.7 on this last one. That's a little not as ovular as the last one. 12 and 8 are pretty close to each other compared to 3 and 1. All right, but I'll do the last one. I'll do eccentricity on this one. Holy crap, that's some big numbers. Quick question, go ahead.
What would happen if eccentricity
You wouldn't have an ellipse, I don't think. It'd just be like all right? Yeah, because the equation wouldn't work out. You could, well, you know what happens when the eccentricity equals 0? You actually have a circle. That's because the radii is the same underneath the x and the y. That one I can answer. Uh-huh. You're killing me, Smalls. What do you need? Oh, okay, I didn't know which one you needed. Okay, so, all right. What do we got to divide both sides by? 3, 2, 1, go. 1225. That's why it's kind of hard to hear you. And you might not be able to see it. I kind of cut these a little too small for presentation purposes. And then I'm just going to not bore you with this. I know the answers from the previous class. 25 goes into 1225 conveniently 49 times. So therefore, 49 goes into 1225 conveniently 25 times. So this becomes x squared over 49 plus y squared over 25. This must equal 1 so we can compare and look at the x and y axis radius separately. All right? And also, this is not a circle because these two numbers in front of the squares are different. When I divide, then I get different radii values. It's really, really, really simple to graph an ellipse. It really should be everybody, no matter where you've been in this class, should have the same results here. What is the x-axis radius? 3, 2, 1, go. What's the y-axis radius? 3, 2, 1, go. Come on, people. First one was a little slow. All right. Square root of 49 is 7. The square root of 25 is 5. They do make this work out nicely for you most of the time. All right. And then let's just go ahead and get all the information. Foci, c squared equals a squared minus b squared. That is 49 minus 25. I'll keep going down here so that we're out of the way of the picture that I draw. That's 24. And then getting good with this, I am covering what you're supposed to know on this when we did the simplifying radicals. Sure, it's 8 times 3, but that's not as good as 4 times 6. What's the square root of 4? 2. So this is 2 root 6 when I ask you to do this in exact form. So the foci are, wait a minute, I can't go too fast. Where do the foci go? Right, left, or up, down? 3, 2, 1, go. Right, left, because it's the major axis. So actually the foci are plus minus 2 root 6, comma 0. You don't put this as a coordinate, you no get or no points. I will mark you wrong. You must write these as coordinates. All right, and then I think I've kind of been being lazy on the vertices and co vertices. So we'll go ahead and write that off to the side here if I made you write them down. The vertices are plus minus 7 comma 0 because that's the x-axis radius going off of the center 0, 0. The co-vertices are 0 comma. You don't put coordinates, you no get or no points. All right, you got to make sure that this is done. And then just for giggles, the eccentricity off to the side here, I'll put it here, then kind of leak into this. I'll circle these. The eccentricity is that 2 root 6 over 7. And then to calculate that, I'll go to my calculator and just, I actually have it up here. So I did the square root of 24, and I got 4.89, and then I divided that by 7. Okay, 0.6998. It really turns into 0.70 when you round this. So this turns into 0.7, and all I want you to understand is that's a little bit less than the last one. So it'll be a little less ovular. The closer to 1, the more ovular it is. But that's why we care about the eccentricity. It tells us about the shape. Okay, but anyway, we can go ahead and graph this. Oh, I'm going to be lazy. 7, 7, 5, 5. I don't know, ballpark. And then to graph the vertices, to graph the foci, I actually needed that square root of 4 thing. Let me go back and look at that. That's 4.89. So, okay, fine, I'll cheat. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4.89 is like right here. So it should be like kind of like right there as well. Not as close to those endpoints. And that's why the eccentricity is a little bit smaller. Okay? All right, now we get these kind of questions, which happens all the time. Now it's the reverse. Write the equation of the ellipse given characteristics. This will go fast. And I do have 8 minutes, so it won't take that long. Give you a minute, though, to write it. Write an equation. We're centered at 0, 0. That's tomorrow's change. Tomorrow we're going to change the center. Okay, remember what vertex and co-vertex is. Which way is this? Is this short and wide? Or is this tall and skinny? 3, 2, 1, go. Good. That wasn't so good first hour. That was much better second hour. Vertex is 0, negative 10. That means 0, down 10. And then, that's what, I'm not graphing it though. We're running out of time. So what you have here is this. It's an x squared plus y squared equals 1, where the y-axis radius is bigger than the x-axis radius. What goes underneath x squared? 3, 2, 1, go. 36. This is simple Simon stuff. That is the radius value. It's the radius value squared that goes underneath there. What's the y-axis radius value? 3, 2. I'm sorry. What's the number underneath y squared? 3, 2, 1, go. A hundo, and that's it. I only gave you one vertex. The other one is 0, 10 up. So 0, -10. Oh, 0, 10 then. 6, 0. Oh, -6, 0. Then I could make the drawing. Moving on. If we don't get that, I don't know what happened with the previous notes. Okay, vertex. What is that? Is that A or B? 3, 2, 1, go. It's actually A. It's telling you that that's the longer one. So which one is this? Short, wide, or tall, skinny? 3, 2, 1, go. Short, wide. As a Federmact, you already know one piece of information. What goes right here? 3, 2, 1, go. 16. But I don't have the other information. What letter is focus? B or C? 3, 2, 1, go. C. So I got to get that magic formula out to make those comparisons. To find B from that C. Square root of 7 squared is 7. A squared is that 16. And now I need to find B squared through a simple solve. Subtract 16, and you should get a negative because it's equal to negative B squared. So this turns positive, and then guess what? What goes underneath y squared? Is it 9 or is it 3? 3, 2, 1, go. It's 9. That's the number that I need. I need the radius squared. Sure, the radius is 3 up and down, but b squared is what fits in the equation to get your formats taken care of. So I really don't have to go any further. I got b squared, and that's what belongs underneath y squared. The y-axis radius squared, which is 9. Okay, co-vertex and a focus. What does co-vertex mean? A or B? 3, 2, 1, go. Oh no. Wipe that bad math out of your brain. It's B. Okay, it's the non-longer side. So you do kind of have to know that as far as how you fill in the formula. Okay, real quick. Is this short, wide, fumble? Just short, wide, or tall, skinny? 3, 2, 1, go. Ooh, I heard a mixed mosh, but I heard most people say tall, skinny. It's tall, skinny because the co-vertex is the shorter vertex, which is going right, left. So it's a longer vertex going up and down, or longer radius is what I meant to say. Another fumble. And then there's another reason. The focus is always on which axis? 3, 2, 1, starts with an M. 0, go. Major. And the major axis is being identified as going along the y-axis. That's another reason why we should have said tall, skinny right off the bat. Anywho, it's this magic formula, and then we can fill in the parts. Minus C must be smaller than A. So it's 6 squared, which is 36, equals A squared minus, okay. You plug this in, first of all, for the love of dog, a negative squared is a positive. I'm sick of that mistake. Number 2, 3 squared is 9. Root 5 squared is 5. What's 9 times 5, everybody? 45. Know how to square a multiple like thing, a product. You square both parts of the products. Okay, so that's how you get 45. And then ultimately you add. No, you don't make this minus a negative plus a positive. That's a PEMDAS violation. PEMDAS violation. And I think that's 81. So here we go. I already squared 3 root 5. Another fumble. Oh my gosh, everyone's just fumbling all over the place. It's like a Bears game. All right, so we get 45, that radius squared underneath the x squared because it goes right, left. And then this is 81. And that's all she wrote. All right, and then we could graph it up, down, 9 for the vertices, plural of vertex. All right, should be very easy. All right, and then hopefully you understand why I did what I did up in the board so that these formulas are more memorizable. That's a word. Oops, that's not what I wanted. Trying to get rid of my